Now that we have established essentially all the fundamental rules of nomenclature, we're going to take a more in-depth look at naming and using a systematic approach for naming. And since we now have all of the different types of complexities, almost at least, that we're going to encounter in nomenclature, it makes sense to do it now. And this will be a good exercise for those of you who are still struggling, and one that if you've already figured out nomenclature pretty well, you probably don't need to watch. But if we wanted to break naming down into steps, the first thing that we want to do now is to see if there's any important functional groups that will define the suffix of the name or the identity of the molecule. And then to identify the longest continual chain of carbons that has those functional group, that functional group or those functional groups, and to make a name for it. Then we're going to add the suffix for the functional group, if that's part of there. That means then whatever's left over becomes substituents. We're establishing a numbering system, which could be based on giving the functional group the lowest number, and if not, then the lowest overall possible set of numbers. Then we'll arrange our substituents alphabetically. We'll add prefixes like di, tri, etc. for how many of substituents that we have more than one of are present. And then we'll add numbers to our molecule, to the functional groups, first of all, if we have any, that is, and also to the substituents. Finally, we'll look for stereochemistry like cis-trans isomerization or chiral centers, and we'll add those designations if applicable. And this all works a lot better if we have an example to go by. So we're going to shrink those rules down a little bit, and we're going to look at a couple of examples. First, let's look at a molecule that doesn't have any rings and doesn't have any stereochemistry evident. If you want, you can pause the video now and give this a try yourself. Now, following our set of rules, the first thing that we would do is to identify any functional groups that are present. And in this case, we have alkyl halides, which are good to know in terms of identifying reactions, but for naming, they're just going to count like regular substituents. The next thing that we want to do is to identify the longest continual chain of carbons, and if possible, with the functional groups. And that will be 1, 2, 3, 4, 5, 6. And we name that chain, and that will be hexane. And when we have an alkyl halide functional group present, we don't do anything to modify the name. We simply use the alkane name. So now we want to see what we have not covered with hexane. We have one ethyl group. We also have 3 chlorines. And we want to establish a numbering system. It doesn't matter in this case whether the numbers go to chlorines or ethyls. We just want the overall lowest set of numbers, which if we number from left to right would be 2, 2, 4, 4. And so that's going to be better than the alternative, which would be 3, 3, 5, 5. And so that we're establishing just the overall lowest set of numbers. The next thing that we'll do is to arrange our substituents alphabetically. So in this case, chlorine, C for chlorine becomes before E for ethyl, so we'll put chloro. Notice chlorine becomes chloro as a substituent. And ethyl. and that we want tri in front of the chloro because there's 3 of them. And then we want to add the numbers. So we have 2, 2, and 4 dash trichloro. Now notice that we do put the 2 twice to distinguish this molecule from a possible constitutional isomer of 2,4,4 trichloro. So we can't just put 2,4 trichloro because that doesn't tell us which of those numbers we have more than one chlorine at. So 2,2,4 dash trichloro dash 4 dash ethyl hexane. And note also that the last thing that we want to do is take a look for stereochemistry, which we said in the beginning we didn't have any of in this molecule, but we're just looking for wedges and dashes. We're also looking for cis-trans isomerization. Don't have any of that in this compound, so we're done. We're going to look at a more complex example next. And this one's made more complex by the fact that we have a ring, multiple substituents including an alcohol functional group, and wedges and dashes, which means that we likely have stereochemistry. And if we just start working through our system, we're looking for functional groups. We have an alkyl halide, but our defining functional group is the presence of the alcohol, which is going to affect our numbering and the name. Now we want to identify and name the longest continual chain of carbons that has the functional group, in this case the alcohol, and ideally the bromine as well. Now it's worth noting at this stage that we could count 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's tempting. But we don't want to do that for 2 reasons. First, it doesn't include the alcohol. And second, we have included a carbon here that is in both the ring and the chain, and therefore would be double counted, and we can't do that. So what we want for our longest chain then is not that, but rather the ring, which has 7 members. So that's heptane. Because of the alcohol functional group, we're going to drop the E and we're going to add an OL for heptanol. Now we want to, and that's adding the suffix, number 3, we want to identify the substituents. And in this case, we've got a bromine, and we also have 2 4-carbon chains. So we've got 2 butyl groups, and we have 1 bromo group. The next thing that we would do is to establish a numbering system, and here we've got to give the lowest number to the defining functional group, which is our alcohol functional group. So when we're numbering, that alcohol group has to be the number 1. And so we could go 1, 2, 3, 4, 5, 6, 7. That would put substituents at 4, 4, and 7. Or if we number the other direction, we'd have 1, 2, 3, 4, and 5. And so our numbering systems for the substituents would be 4, 4, 7, or 2, 5, 5. And tough call here. Notice that the second set has 2 out of the 3 aligning numbers being smaller and would be preferable. But this would also be a very difficult one for us to distinguish, and so if we did it the other way around, that would not be a particularly big deal. And just let's move that number comparison out of go with the bottom set, which is going to give us the lower set of numbers overall. And so we want to next arrange our substituents alphabetically. And so Br for bromo comes before Bu for butyl. So we'd say bromo, and then we'd want di for 2-butyl for the 2-butyl groups. We would add prefixes, specifically the di to the butyl. And then we want to add our numbers in. So the bromo is at the number 2, and the butyls are both at the number 4. And again, we write the number 4 twice, even though in this case, if you just put 1 4, it would be clear. We're just following the procedure. And in this case, to be absolutely correct, we want to put the 1 for heptanol. Although it's worth noting that sometimes you wouldn't see the heptanol, the 1 for the heptanol, because if it's a ring, which means it shouldn't be heptanol, should it? It should be cycloheptanol. Any rate, because the 1 is in a ring, and the lowest number has to be that group, it's always going to be 1, and so occasionally you'll see that 1 in a ring where it's the defining functional group left out. And that, I suppose, is people rebelling against the nerds in Switzerland and saying, well, it's just obvious that that's what it is, and so we're not going to bother. Now, the last thing that we need to do here is to look for and account for our stereochemistry. And in this case, we do have a pair of chiral centers. The carbon, the number 1 carbon that the OH is on, the number 2 carbon that the bromine is on. And so we need to assign those absolute configurations as well. So in order to make more room for that, though, we're going to redraw the molecule extra big and drop the naming rules to make room for it. So here's our molecule big enough to fill the whole screen. Let's first look at the chiral carbon that has the alcohol group, and let's draw in the hydrogen here that is also present. Now, if you want to, pause the video now and see if you can assign both that chiral center and the one at the carbon here that bears the bromine. And if we bring our attention back to the top chiral center, we have a hydrogen, an oxygen, the other chiral carbon, and a third carbon in the ring to consider the priorities of. And the hydrogen, of course, is always going to end up being number 4. The oxygen is going to beat the 2 carbons. And then we have a tie, right? So we have to consider what each carbon is attached to. The carbon here in the ring has another carbon and 2 hydrogens attached. The other chiral center here has a bromine, a carbon, and a hydrogen. And so taking the champion of each, the bromine will beat the carbon. And so that means that the other chiral center will be our number 2 priority group, and the other carbon in the ring will be our number 3 priority group. So for our top chiral carbon, we go 1 to 2 to 3. We're going clockwise, but with the low priority in the front. And we say R is clockwise with the low priority in back. S is one thing switched. So this chiral center is going to be S. Now we can add that to the name. by putting an S at the very beginning of the name. And since it's assumed that there are two chiral centers, or it's looking at the molecule, we're going to assume that you put them in order so that this applies to the lower numbered carbon. But if we wanted to be explicit, we could put 1S. Now let's clear up a little bit of our notes so that we can focus on the other chiral center, which is the carbon that bears the bromine. And we'll mark that one in blue. And on this carbon, of course, we've got a hydrogen that's not drawn. That's automatically going to be the lowest priority. We have a bromine that's going to be the highest priority because it's got the highest atomic number. And then we have a pair of carbons. We have the other chiral center up here, and then we have this carbon CH2 group that's in the ring. So we have to then go to what each one's attached to. The other chiral center has an oxygen, another carbon, and the hydrogen. The carbon here in the ring has one more carbon in the ring and two H's. So we take the highest priority of each one. The oxygen of the other chiral center beats the carbon of the CH2. And so the other chiral center is also the bottom chiral center's second priority. So the carbon in the ring here that's a CH2 group becomes the number 3 priority, and on the bottom chiral center we go 1 to 2 to 3, skip 4, back to 1 again. So now we're going counterclockwise, but with the low priority in the back. And again, we say R is clockwise with a low priority in the front, and S has one thing switched, either direction of rotation or the orientation of the low priority group. We're switching this time the direction of rotation, so this chiral center is also S. And so we'll indicate that in the name. We have 1S, comma 2S. Sometimes we'll just put those in parentheses to set them aside from the regular naming. Dash 2, dash bromo, dash 4, comma 4, dash dibutyl, dash 1, dash cyclohexanol. Now, again, note that there are a couple alternatives to that. Specifically, that the end could simply have the 1 omitted and be dibutyl cyclohexanol, or it could be cyclohex and dash 1 dash all.